afternoon, everyone. My name is Yoshi Kamiya from Untitled University. Thank you for being here. So I'd like to thank organizers. Howdy.
Please call me.
Please welcome.
For giving me this wonderful opportunity. Maybe I should call Kawashima 老師。
Sensei. You can say
Sensei. Anyway, so today I'm going to talk about my recent, not very recent, but my work this is about quantum Monte Carlo simulations of interacting Majorana fermions on a square lattice. You may wonder how can one can simulate Majorana fermions with quantum Monte Carlo, but there's some trick that works only in a strong predicament. Okay, but before going to my main topic, let me just briefly guide through you to the Shanghai area. So first of all, you may wonder what 交通 or 交通 means. Actually, it literally means transportation. The university was founded in 1896, just after this war between Japan and China, which was 94 and 95, I guess.
Yeah.
And after that, probably they wanted to improve the society drastically. So that's why they built a few big universities. Actually, this university was founded by the Ministry of Post and Communications of Qin Dynasty. And there's a huge main campus located in the suburb area of Shanghai, right there. Right here. This is more or less a downtown area of Shanghai. This is some famous picture of Waitan here, which is located right here. It takes around 1.5 and 2 hours to get there from this downtown area. Okay, actually next year we're gonna organizing SJTU conference for high frequency magnetism. Probably this campus will be the main venue of the conference, but probably I will remind you later. But there's another small campus in the downtown area. Then even there's a small there's a metro station with that name. But if you come to this station, there will be probably no conference there. So you have to come to this area, which is a bit far away from the downtown area. This is a huge campus. So this is some map of the campus. In the same scale, this is the Hongo campus of University of Tokyo. So it's around at least 2 or 3 times larger than the campus. The gate I have shown in on the start page, it's actually located here. To be honest, I'm walking here, so going from here to here is a very big distance, like going from Hongo Sanchomi Station to Ueno Station or even further. So in everyday life, in everyday life of my, in my case, I just went there just once out of curiosity. And actually, I regret to go there because it's a long distance. Too much exercise even after lunch.
So they have a lake inside the campus?
Yes. We go at a sea lake. It's more or less a pond. Of course, it's not that huge. Okay. Let me give you my scope. I'm interested in the effect of interactions among particles that emerge out of some topological nature of wave function. For instance, as Christian talked about the interaction between spinons in quantum spin liquids that will induce a transition into ordered phase, like a magnetic ordered phase or one on solid phase. And recently, people are working on creating the system of Majorana fermions in some artificial receptor. The Majorana fermions are also some kind of fractionalized particles on the edge. As a consequence of bulk boundary correspondence out of topological state of matter, if you have a vortex, they act like an interface between a topological state and normal state at the core. So therefore, you would expect some edge state, generalized edge state at the core. In some particular two-dimensional superconductor, this is a Majorana zero mode state. So we may wonder what would be the effect between such quasi-particles. Admittedly, this is almost like a science fiction at this level. But nevertheless, we are driven by curiosity to work out such systems. Okay, one possibility may be some new spin liquids or some topological phase transition that may be out of conventional random paradigm, or maybe we have some proximate order phase which may have some neutral properties. Okay, let's move on to the next slide. So this is more or less the setup that I have in mind. Although I'm showing some how can I say, rather specific or seemingly realistic setup, I would say this is still a science fiction, as I mentioned in the beginning. But basically, what is not science fiction at this point is that we may be able to create a single fermion at least in such a setup. So as Fu and Kane proposed in 2008, let's imagine we have a topological insulator, 3-dimensional. We have some surface state. Let's consider some hybrid system with this topological insulator with superconducting state. And due to some proximity effect, we have some topological, some proximate state of two-dimensional topological superconductor. By applying a magnetic field, we can have a Majorana zero mode at the core. So that's more or less one possible setup for such a system. Now let's move on to more exotic idea. So by applying a magnetic field, let's imagine we have a lattice of vortices, like basically a Abulgasov vortex lattice. And then each vortex has a Majorana zero mode. And this is basically the setup of lattice of macroscopic number of Majorana zero modes. And what will be the possible effective interactions that have been there are several pioneering work done by Armin Damari. Actually, he's a friend of mine when I was in Los Alamos. He worked rather hard on this subject and published several papers. Working with Marcel Franz, for instance, they wrote a review article this year. Okay, this is the Hamiltonian that I'm going to focus today. So we're going to focus on Majorana fermionic model defined on a square lattice. This is just the Hamiltonian. We have some hybridized quadratic term of Majorana fermions between nearest neighbor sites, and the interaction is intrinsically off-site type, because the on-site interaction is trivial because Majorana fermion nature. And actually, okay, we can talk about some exotics like non-abelian statistics, this kind of thing. But as far as this talk is concerned, this is almost the only thing that you could see Majorana nature in this model. It would be great to have some lattice system which should reflect some non-abelian nature of the Majorana fermions. But at this point, as far as I can see, this off-site nature of the interaction is the most, how can I say, most visible effect consequence of the fact that we are considering Majorana fermions. Okay.
And can you write a spin model and using the Majorana representation get this Hamiltonian?
That will be the opposite way I'm going to do it. So I'm gonna map this fermions into a spin model to run a quantum mechanical simulation. But that is possible only when this coupling is gone. In the absence of this term, we can use Jordan-Wigner transformation to map this Hamiltonian into a spin model without a non-local term. Okay, let me indulge in a little bit speculative picture for the scope about the scope of my scope. Okay, in the case this is probably the most basic Hamiltonian that we could think of as a as starting from Majorana fermions. In the case of fermionic usual complex fermions, this is a sort of basic model to study high temperature superconductivity. By changing the ratio between the hopping and interaction, you can study the fermionic theory for small weak coupling, quantum magnetism for large coupling, and in between we may have some. Yes.
So as you said, that the triangle lattice is more common for vortex lattice.
Yes.
In case of the triangle lattice, can construct a similar Hamiltonian including 3 fermions?
That would be the actually last comment of this talk. The answer is unfortunately no. It will be great to study the triangular lattice system, but unfortunately there will be a non-local term after applying that method. I'm gonna use it this time. Okay, let me go to this kind of sales talk. So we can also consider both Hubbard model, which is a much simpler model. But nevertheless, this basic model have served as sort of guidance for experimentalists doing working on cold atom systems. You can have superfluid state for small u. You can have Motto insulating state for large u. And in between, we have superfluid Motto insulator transition. Then, what about if we change the particle into Majorana fermions? What states of matter can emerge in such many varied systems? As I mentioned before, the community is not that big yet. But nevertheless, there have been several studies, mostly in one-dimensional system. Because basically, the main observation so far is that by using Jordan-Wigner transformation, starting from such Majorana Hamiltonian in the beginning, typically the spin Hamiltonian you get looks quite exotic in the context of quantum magnetism. So you may expect some new phase in such a spin Hamiltonian. That has been the kind of driving force in the community. So they have been studying Majorana chains. They also study ladder system. They also study square lattice system before, and that is also case with ourselves.
But in principle, this could also be motivated by some triplet superconductors. If you take pairs of these real fermions, convert them in complex fermions, you will have some Hamiltonian for triplet superconductivity with interactions.
That's right. Yeah. Okay. Now, in this talk concerns a square lattice case, as I mentioned. In the strong coupling limit, where the hopping is 0. And you may actually the one difference from the fermionic Hubbard model is that even in this strong coupling limit, the Hamiltonian is not classical because of this off-site nature of the interactions. You can see that the placket coupling of this one, placket coupling on this adjacent site, adjacent bracket, sharing just one node. They do not commute with each other. So it's a quantum mechanical Hamiltonian. But you may wonder, how come we should bother such a strange-looking Hamiltonian? In the context of Fulking model, these people have argued that actually it is possible to tune the interaction strengths, relative interaction strengths, to bring the system into a strong coupling limit. This is just the quadratic Bogoliff-Dujan Hamiltonian for the surface system, subject to the superconducting proximity effect. And we have two cases basically, which are different in terms of symmetry. In a generic case where the chemical potential in F is different from 0, symmetry class is D. But okay, we can assume the chemical potential to be 0. That's looks very special, but probably we can, in principle, one may use some gate voltage control to the chemical potential at the surface. That is more or less the argument. But the consequence of this tuning, fine tuning, is that there is an additional artificial time reversal symmetry, which can be written in this form. And the consequence of this symmetry is that the quadratic term acquires minus sign after this transformation. So therefore, when someone can tune the surface chemical potential to be 0, basically quadratic term is prohibited by symmetry. So at the quadratic level, a number of vortices coincide with number of minor fermions, which has been known in the context of high energy physics. According to the literature, there's a model which is called Jacques-Rossi model, which has basically the same, which dealt with basically the same problem. Okay. So although our community is not that big yet, there have been previous studies that worked on the same problem. Ian Affleck and his collaborators so far worked on mean field theory. They also worked on some RG type calculation later on. But first, they use a simple mean field theory. What they found is that in the strong coupling regime, where G is much larger than T, there's a tendency for minor fermions to be paired up. This is some cartoon picture of the mean field result. Basically, neighboring minor fermions form some complex pair to become a complex fermion. They form some sort of dimerized phase by breaking the translational symmetry and rotational symmetry. Okay. At this point, this state may look quite natural, right? We are adding some hybridization between minor fermions. Okay, you may have something like that. But actually, apparently, this innocently looking conjecture by mean field theory was challenged by numerical study based on ED. Okay, these guys formed exact diagonalization on the strip geometry of this strip geometry with four modes in the vertical direction, up, and they can change the length of the strip up to 16 modes. There are some hidden symmetry, so they can go to this relatively large system size. They worked on strictly in a strong coupling limit. They forget about the hybridization term, because actually the same author who claimed that by tuning the gauge potential of the surface, we can realize strong coupling Hamiltonian. They also introduced some artificial modulation between two brackets on even lows and odd lows. And what they found is the following. So basically, by changing ratio between G1 and G2, they computed the hybridization of this nearest neighbor by the fermions like this. Okay, to be honest, to my surprise, they claim the continuous phase transition based on this calculation. So basically, they compute, as I say, basically they compute the density of complex fermion by changing the ratio between G1 and G2. And what they claim is that around the point where G1 and G2 are equal, this seems to be this so-called order parameter seems to vanish quasi-continuously. Okay, and this is some conjectured phase diagram. Horizontal axis is the ratio between G2 divided by G1, as in the previous slide, and the vertical axis is the chemical potential. In the current context, they correspond to the kinetic energy. This is some cartoon schematic phase diagram they proposed, they conjectured. Okay, this is a line with strong coupling limit we want to focus. Based on this ED calculation, they claim that this point, the strong coupling system with equal homogeneous coupling may be located exactly at some topological quantum critical point, which is actually apparently contradicting with the mean field type argument. So we wanted to reconcile this issue.
Usually, what is C? C just one.
Right. So the sorry.
Sorry, C. Yes. C plus one.
Oh, I see. So okay. Here, away from the strong coupling limit, they just basically worked on mean field theory. Then they are Chern numbers. Okay, what we can do, and then we realize that we can map the system into a spin model, for which apparently we can use conventional quantum Monte Carlo technique to study sufficiently large system. This is how it works. Basically, okay, we introduce conventions for pairing. This is nothing but has nothing to do with the dimerization. Just a convention for pairing Majorana fermions into a complex fermions. We define complex fermion C for each vertical pair of Majorana fermions like this, and then we perform two-dimensional Jordan-Wigner transformation by introducing the site ordering like this. Okay, sorry for screwing up, but like this. And what we can realize immediately is that since we don't have this kind of hopping term between different chains, I'm talking about this as a chain, I'm talking about this as a different chains. Since we don't have a hopping between different chains, basically there's no local factor after this Jordan-Wigner transformation. The only type of term that we have in the Hamiltonian is quadratic in Majorana fermions. And we have two fermions, for each interaction term, we have two fermions on each chain. So basically, this pair of Majorana fermions behave like a bosons. So because of this artificial pairing that I have introduced, originally these two bracket interaction, these bracket interactions are of the same ones, but because of this artificial conventions, after the transformation, they look differently. This bracket interaction becomes Ising term between different chain, different cross, SX, SX. This bracket term becomes a forced-in bracket term in the language of quantum spins. Okay, this is the Hamiltonian. The interaction between this interaction is only along the horizontal direction, and for each bracket we have a force in term of Sx. Because of the sign that I have chosen, there's no sign problem when we apply one-line Monte Carlo symmetry.
Excuse me?
Yes.
So when we map the spin model to fermion,
Yes.
we need some constraint to restrict the Hilbert space.
No. Because this okay.
But here, yeah. So it's actually
It's a transformation. It's a faithful transformation. So to repeat, so we have a minor fermion at each site.
yes.
So okay, I want to define one complex spinless fermion for each pair.
Okay.
Okay, this is the spin Hamiltonian. As I mentioned, there's no sign problem, so we can perform unbiased simulations with only statistical errors, and the established methods, developed by many other previous researchers, developed in many previous papers. We use specifically efficient worm algorithm. We can access to a much larger system compared to ED calculation. It can go up to 60. So in terms of the number of minor modes, we can deal with 7,000 minor modes, which is significantly larger than the one in previous ED study. Okay, in the end, this is the result of QMC after Jordan transformation. I'm showing the specific heat as a function of temperature scaled by the G. G is the coupling constant, which is the only energy scale in the model. So, okay, as you can see, we observe some very clear signature of finite temperature transition. Okay, there's some broad peak at higher temperature. However, the peak height of the peak at lower temperature grows as the system size increases, like this. And furthermore, this state of this field, suggests a gapped nature of the ground state, which contradicts with the previous claim of topological content criticality.
Sorry, I forgot the definition of parameters.
Sure.
You are studying this at the supposed critical point?
Yeah, that's right.
Did you study other values of the parameters?
Not yet, but after okay, in the coming slides, I can tell some duality mapping, which clarifies the meaning of this changing the ratio G1 and G2 more clearly. Basically, it's okay. Yeah, let me come up to the point later. And what is the nature of the phase transition? That is the question, right? Okay, you may wonder, this so-called spin may develop some order, but actually this is impossible at finite temperature. There are a bunch of one-dimensional symmetries, which is a peculiarity of the strong coupling. For instance, we can take a product of sigma x along horizontal axis. They commute with Hamiltonian. Basically, they flip all spins all together. Therefore, the sigma z z component of spin cannot develop the long-range order along the vertical direction. So, in a sense, there's a dimension reduction in terms of this order parameter field from 2D to 1D. So therefore, sigma z spin, at least by itself, cannot order at finite temperature. And here comes the duality mapping. So we are wondering what was the nature of the order phase. And okay, we worked out for a couple of months to figure out this mapping. Actually, we can map the system to a quantum compass model on a square lattice. The changing G and G2 correspond to changing the ratio between horizontal coupling and vertical coupling. And this is how it works. One quick observation is that we can perform some sort of checkerboard decomposition of the Hamiltonian. Okay. what I mean is that we can decompose the bunch of interaction into two sets. What we can see is that interaction in one subsystem in this set commute with each term in the Hamiltonian on the other set, because they share either zero mode or two modes. So they commute with each other. So we can treat them separately. And after some complicated, I can discuss you if you want. But there's a two-step Kramers-Warnier transformation that brings the spin Hamiltonian that we simulated directly into the quantum compass model that looks like this. And there's a one-to-one correspondence between the term in this quantum compass model and the original Majorana-Fermion bracket operators. Basically, this is the site of mu spins, which is a basic degrees of spin 1/2 degrees of freedom in the compass model. And the interaction between these two spins correspond to the bracket interactions that this bond overlaps. So basically there's a one-to-one correspondence in terms of operators, and they satisfy the same algebra as required in the duality mapping.
So G is different on the plaquettes with different color, is that correct? The G1 and G2 color?
No. Here I additionally decompose the Hamiltonian into two sets.
But G1 and G2 then are what the interactions are like? So
Okay, I have to come to Oshikawa-san's point. Actually, I made sorry for interrupting. I noticed that I made some incorrect statement about the question. Sorry, I'm screwed up, but I come to later. So come back to the question. So we decompose the whole Hamiltonian into sum of two subsets.
yeah.
And G is like I have only one interaction.
Only one coupling.
And changing G and G2 correspond to making them inequivalent.
These two, A and
A and B.
So your previous spin operators are sitting on bond centers, right?
Yes.
And this new operators in compass model sitting on plaquette centers.
Yes.
So what is the relationship between sigma and mu's?
Okay. Now I need to explain the two-step Kramers-Warnier transformation. So this is a mess.
Okay, so it's a kind of the classical Kramers-Warnier transformation.
Yes.
Okay.
But okay,
It's
we
a kind of version of the Kramers.
right. But we do in two steps. So first I introduce some this kind of ordering, and so I first.
But anyway, my question is the relationship between the sigma spins and the mu spins are not related by local transformation.
No. Yeah,
It's
a local transformation.
It's a very non-local.
Yes. Yeah. So basically, we first introduce some dual spin on the center of the vertical bond. Then I introduce another dual spins between two dual spins, which bring us the last dual spin at the center of each bracket. And okay. The advantage of this duality mapping is that we can use the established knowledge about the compass model to interpret our results, which looks puzzling. Okay, according to previous studies, it has been established that the compass model undergoes a so-called nematic transition. at any finite temperature, the spin-spin correlation function is short-ranged. However, there's some Z2 symmetric breaking associated with spin lattice combined rotation. Basically, changing X component to Z component and simultaneously rotating the lattice from by 90 degree. Right. And this is the order parameter. Order parameter is basically the difference between energy density associated with horizontal bond and energy density associated with vertical bond. So in our language, this should be the difference between energy density associated with one plaquette and with respect to the energy density associated with neighboring plaquette, like this. So what would you expect is this kind of some modulation at low temperature, modulation of energy density at low temperature. Okay, at high temperature, okay, I'm picking up only one subset of A and B because they are sort of decoupled each other. So at low temperature, they become inequivalent. By spontaneously breaking symmetry, one plaquette tends to have lower energy, and the other plaquettes tend to have higher energy. This type of plaquette modulation occurs independently between A and B sublattice. The consequence of the transition is G2 cross G2 type, but in a decoupled, completely decoupled manner. Like in the case of Ashkenazi Hamiltonian without any coupling between them. I'm talking. Okay, this is my A sublattice. This is my B sublattice. We can think of this kind of pattern or this kind of pattern. For B sublattice, likewise, we can think of this kind of pattern or this kind of pattern. The four different combinations correspond to these four different patterns. We have some stripy feature like this, or like this, or like this, or like this. Okay. And one last comment about this result is that here I'm talking about the energy of plaquette. We cannot think of that, the density of complex fermion associated with each side because the boundary symmetry that I mentioned. Now I can think of a situation away from strong coupling limit. We have some small amount of hybridization between dimers, horizontal, either horizontal or vertical direction. Since we are starting from this kind of state, you can imagine some ferro type ordering, which is precisely predicted by the mean field type argument. Okay, to check, this is the result, QMC result of so-called order parameter. Based on our knowledge obtained by duality mapping, we can cook up sort of order parameter like this. This goes like this at low temperature. We observe some sizable finite size effect. I think this is due to open boundary condition that I kind of impose to perform the two-dimensional Jordan transformation. Excuse me. Jordan transformation. This is the winter parameter. It shows once again there's some sizable finite size effect, but there's some crossing point around temperature which is maybe 0.25, which coincides with the peak position of the divergent specific heat.
Sorry, I have a little bit confused. The model itself is already decoupled to system.
at the operator level, yes.
Yes.
But at the level of Hilbert space, no.
Yeah, yeah, yeah. Okay. And each how can I say system had the G2 symmetry.
Yes. Okay.
The parity of the number of fermions is conserved, right?
It's a remaining one-dimensional symmetry.
Right, so then even if you use closed boundary conditions, I mean, because the parity is conserved, you could deal with it.
I was too lazy to take into account this parity conservation. By using this additional symmetry, actually we could simulate the system with periodic boundary condition as well. Okay, in the end, the mean field theory seems right. Then I want to review their mean field result a little bit more. Actually, the predicted transition is a little bit interesting. I want to show this is the mean field result away from strong coupling limit, because away from the strong coupling limit, we cannot deal with the system in the same technique. So I just want to repeat actually the mean field result, what's going on. I mean, it's a sort of review. Okay. Now we are introducing the hopping, and also I'm introducing the difference between P and J. The interest is at the point where P and J are equal to each other. And here I'm showing the D is a sort of order parameter, and this corresponds to actually the gap of the Majorana fermion at the mean field level. What we can see is that D closes as we increase the hopping hybridization. In the strong coupling, we have gap to dispersion, but this seems to be closed as we introduce the hybridization, like this. And beyond that, they have Majorana cones at X, some boundary of the past V and so on, like this. And what is a little bit interesting is that below this quantum critical point, we have a gapless Majorana excitations, but simultaneously the system recovers the symmetry, translational symmetry, which has been spontaneously broken in the strong coupling limit, seems to be recovered at the same critical point, TC. That's at least the claim at the mean field level. And actually, Affleck and his collaborator worked out some RG type analysis, and what the claim is that this quantum critical point may have some special supersymmetric properties. Okay, I came to the final slide. What we study is the Majorana-Hubbard model only in a strong coupling limit. We conclude that the system undergoes some Finite-temperature transition, or some discrete symmetry breaking, which is different from the previous claim of criticality. Away from the strong coupling limit, we expect a diagonalized space that has been predicted by mean field theory. So, admittedly, the information that we could add is not that much, but I hope at least the part of my talk might be interesting for you. With that, thank you for your attention. I forgot to mention, but they are my collaborators. Akira was my previous boss at Riken. Yeah, he has been kind enough to make me stay there for many years, 4 years, I guess. And Jeffrey and Jawei are my collaborators in Virginia, University of Virginia. And I can take any question.
Yeah. If you
consider the hopping term as a perturbative term, then what kinds of term is obtained in the language? Yeah, okay, okay. So let me go back to. So obviously, it's not, I don't want to include this hopping. And since we are starting from the stage which breaks the symmetry already, probably okay, we can forget about. Okay, how can I say? So basically, the part of the term coming from the hybridization is just a magnetic field for the in the spin language. So let me see. Yeah, maybe that it becomes some non-local. That's okay. So there are some terms that become non-local. Okay, to be honest, I cannot treat them on equal footing. But how can I say? So we start from a situation in which the product of this guy and this guy is, let's say, one. They tend to be empty, or occupied. Now I'm including the part of the perturbation includes, favors occupied state, for instance. Then I would expect this kind of decoupling in the physical sense as well. That's a kind of hand-waving argument.
Yeah, right.
Can you remind me of the original model?
Sure.
Parameter TGM.
My pleasure. Yeah, like this.
And by strong coupling, you mean G bigger
Yeah.
than T?
Yeah. Actually, T is 0.
Okay. And then in the middle, first you show the predicted phase diagram from mean field or something. And then there is some Chan number 0 to 1 to 0, critical points. Yeah. And so at G1 equals to G2, there was supposed to be, in this figure, strong coupling limit is horizontal
Yes.
axis.
Yes.
And then at G1 equals to G2, there is a predicted critical point.
Right.
And your calculation reveals that this point actually belongs to gapped phase with some symmetry breaking.
Yes.
So how this phase diagram is modified in your picture? So there's a finite region of symmetry broken in origin.
Yeah, I would expect so. So we start from this gap state, right? By changing the ratio between G1 and G2 corresponds like a pretty magnetic field in 2D Ising model.
Oh, I see.
So there's no spontaneous symmetry breaking, but we have gap state. So this means gap state. By argument of continuity, I would expect a gap state around here. Now that in the slide of mean field theory, what I show is that the gap seems to be closing as we increase the hopping T. At some point, gap seems to be closed, and the symmetry, lattice symmetry is simultaneously recovered.
So this blue phase of boundary
Will be kind of somehow pushed up, like this. That's the kind of picture.
So you have phase diagram, boundary like this, and
and
in between you have gap.
Yes.
And only at G1 equals G2 you have spontaneous symmetry.
Yes, as a function of temperature.
It's kind of ordered phase of Ising model.
Yes, exactly.
Changing magnetic.
Exactly. So universal equality is the same.
So I think a related question. I think in the mean field phase diagram there's a supersymmetric point. Did you find this in your calculation?
In my calculation, I couldn't access to that point. in my calculation, with our method, we could not access to that point. But the supersymmetric point is a point at which this rotational symmetry is decoupled, and simultaneously gapless fermion appears, which is supposed to around here and here. And that's a picture.
So you mentioned that once you put a finite t in this nematic phase, so let's say G2 is equal to G1, now you will have this dimerized order parameter.
Yes, yes.
So what is that in terms of the spin model that you wrote? What will be that dimerized order parameter?
It's simply sigma z. Sigma z.
Sigma z. I see. So and why is it? It is so obvious that it will appear. I mean, are you breaking one of these 1D-like symmetries, or what is happening?
Yeah, 1D-like symmetry is gone.
Is gone. So then the leading order parameter that will be only one spin operator becomes.
Yeah.
I see. That is.
Yeah.
I see. So you go from nematic to magnetic,
Yeah.
essentially, because you break that 1D
That's right.
symmetry.
That's right.
When you say there's a Z2,
Yeah.
and you say it's decoupled,
Yeah.
so are all sorts of possible coupling terms in the effective field theory like gone at the critical point? Can you like say it in a way?
You
like
mean
that?
away from the strong coupling? Yeah. Away. If I understand correctly your question, away from the strong coupling limit, this decoupling will be gone.
Okay, so it'll be coupled.
Yeah.
Okay.
I think the situation is similar to, once again, Ashkin-Taylor model at finite temperature.
So do you mean you expect Ashkin-Taylor type
Yeah.
universality in
Yeah.
those?
Yeah.
Okay.
At least naively.
I see.